So in last lecture, we have proved one theorem. If x has the chi-square with 1 lambda, that is non-central chi-square with 1 lambda, the lambda is a non-centrality parameters, and y is distributed as a chi-square with m degree of freedom, then u is equal to x plus y is nothing but the chi-square m plus 1 with non-centrality parameter lambda, provided x and y are provided x and y are independent. So the same additivity property of the chi-square distribution is continue with the non-central chi-square. If any one of them variable is a non-central chi-square, the sum of two independent random variable is also a non-central chi-square by the sum of the corresponding degree of freedoms. So that we have seen in the last lectures. When I told you that you have to solve this example, we have used the uh, polar transformation methods to prove this theorem or to prove this property. And I told you that you have to use the Jacobian approach to solve this particular equation by for this property by considering u is equal to x plus y and v is equal to y, which implies x equal to u minus y is nothing but x equal to u minus v and y equal to y. So you have to find out the Jacobian of x to y, xy to uv, and at the end of that you will show that it has the chi-square distribution with m plus 1 lambda. I hope you did it, because as I told you that whatever I am giving in a homework, that is you have to submit as a part of assignment, and I will give the date of a submission of assignment prior to only 3 days or 4 days. So keep solving all the examples. Okay. Now we will see another theorem. If x1, x2, xn are independently distributed,
Sir, can you please speak little louder?
normal mu I sigma square, then y is equal to summation I running from 1 to n xi square upon sigma square is distributed as non-central chi-square with n degree of freedom and non-centrality parameters. Lambda equal to summation I running from 1 to n mu I square upon sigma square. Okay, so earlier we have shown if x has the normal mu sigma square, then y is equal to x by sigma square as the chi-square distribution with one degree of freedom and with non-centrality parameters mu by mu square upon sigma square. Here we have given the n independent random variates which are randomly drawn from the normal distribution whose mean is mu I and constant variance sigma square. Then we wish to show that the distribution of y, where y is summation xi square upon sigma square, summation is running from 1 to n, is chi-square with n degree of freedom. Why? Because there are n independent random normal variates, and because of the mu is not zero. If mean is zero, then the y is equal to summation xi square upon sigma square has the central chi-square with with n degree of freedom. But here mu is not zero, so therefore the distribution becomes the non-central chi-square, and because there are n independent variates, so sum of the square of n independent variates is a chi-square, but because mu is not zero, so it is a non-central chi-square with n degree of freedom, and non-central parameter is nothing but the lambda is equal to summation I running from 1 to n mu I square upon sigma square. So we will solve this or the give the proof of this theorem. We have given that xi's are normally independently distributed with mean mu I and variance sigma square, where I running from 1 to n. So that is given to us. Therefore, the joint density of x1, x2, xn is given by, so I am not writing the 1 upon root 2 pi sigma. Okay, let me write. Okay, given by f of x1, x2, xn, x1, x2, xn is nothing but product of n independent random variables. It is f of xi, xi. But we know that xi has the normal distribution, so it is nothing but the product of I running from 1 to n, 1 upon root 2 pi sigma e raised to minus half sigma square xi minus mean is mu I, so it is a mu I square. Now I am writing this part as a, let us say, constant. So it is I running from 1 to n e raised to minus half sigma square xi minus mu I square, where constant is 1 upon root 2 pi sigma power n. Okay, because I am not interested in that, so I just write it as a constant. It is a constant into, because this is the product of the independent random variate and the power is, the base is constant, then of course it is a sum of this. So you can write this as a summation I running from 1 to n xi minus mu I whole square. So this is nothing but the joint density of x1, x2, xn. Okay. Now, because we have seen the concept of orthogonal transformation, okay, so we will use the concept of orthogonal transformation. Let us make orthogonal transformation let us make orthogonal transformation y is equal to bx, okay, where b is nothing but the orthogonal matrix such that bp transpose equal to b is of a n cross n, and which satisfy bb transpose is equal to identity, and because it is a complete orthogonal, so it is a b transpose b is equal to b also, and that is identity. Okay, so b is n cross n orthogonal is an orthogonal matrix whose first row is mu1 upon mu, mu2 upon mu, up to mu n upon mu. Okay, when it is a orthogonal matrix, so as I say that complete orthogonal matrix is a orthogonal by row. Its rows are orthogonal as well as the columns are orthogonal. So when you multiply row with itself row, then what happens? It is a unit value. So therefore, mu1 upon mu n upon mu, this row multiply itself as a row. So we know that this answer is 1 because of the property of a orthogonal matrix. So what happened? It is a mu1 square upon mu square plus up to mu n square upon mu n, mu square is 1. So which implies we can write summation mu I square, I running from 1 to n. This mu square is constant and we take in the right hand side. This is the we have. So when we whose first row is this with summation I running from 1 to n mu I square equal to mu square. So why it is a mu I square equal to mu square? So that justification I have given here. This is the corresponding justification. Okay. So we consider the y as orthogonal transformation of x, whose first row is mu1 by mu, mu2 by mu, up to mu n by mu, with mu square equal to summation mu I square. Now, remember what we wish to find out? We wish to find out the distribution of I running from 1 to n xi square upon sigma square. Okay. So we will proceed in that way. Now, what is given in the joint density? It is given this quantity. So let us use this quantity first. Summation I running from 1 to n xi minus mu I whole square is equal to, you can write it is a summation I running from 1 to n xi square minus 2 times summation I running from 1 to n xi mu I plus mu I square. Can we write? And because of the summation outside, so it is a summation I running from 1 to n. But we know that when you take the transformation, x is, the elements of x are normal, independent, 0, 1. And if you take the transformation y is equal to bx, then x transpose x equal to, you can write as a y transpose y. So what is x transpose x? It is a summation xi square. So you can write here it as a summation yi square, I running from 1 to n. Okay. And what about this 2 times summation xi mu I equal to, what can you write? Can I write 2 times mu into y1? And this mu I square is nothing but summation mu I square. Can I write it as a mu square? Because I have written this. Now I will show why I have written the 2 mu1 y. I'll give the justification. Here the first row, what is the transformation? Y is equal to bx. So what is the first row of this matrix? It is giving the first element y1. So it is first row is nothing but mu1 upon mu up to mu n upon mu, and here the element of x is x1, x2, xn. So what is y1? Y1 is nothing but summation mu I xi upon mu, I running from 1 to n. If you just take the mu this side, you will write mu y1 equal to summation xi mu I. So what happened? I have just substituted this xi mu I by the mu y1 by using this. Okay, is that clear? Okay, so y1 square summation yi square is equal to, can I write it as a y1 square plus summation I running from 2 to n yi square? I can write, and this is 2 mu y1 plus mu square. So I'm just using y1 square minus 2 mu y1 plus mu square is nothing but y1 minus mu whole square plus summation I running from 2 to n yi square. Now substitute the value of 2 star in star. Substitute value of 2 star in star. We have joint density of y1, y2, yn is nothing but it is a constant into e raised to minus half sigma square, and you can write summation y xi minus x bar square is equal to y1 minus mu square plus summation I running from 2 to n yi square. Okay, that you can write. So it is nothing but, you can write it as a e raised to minus half sigma square y1 minus mu square into product of I running from, because it is a summation, so power is base same. So you can just take outside, it is a summation I running from 2 to n e raised to minus 1 by 2 summation yi upon sigma whole square. Okay, so that you can write. So based on this two, this is a one. Of course, constant is outside. Okay, so this is the two, the density of two different variable. So here we can say it has the y1 is nothing but normal with mean mu and variance sigma square. However, yi is nothing but it is a normal, because here minus mu is not there, so it is a 0, and variance sigma square I running from 2 to n. Okay, so it is a nothing but the joint of a random variable y1 and y2, yn. So it implies that y1, y2, yn. You can see that y1, this whole y2, yn are independent. Okay, these are normal independent. So this y1 has no connection with y2, yn, so all are independent. That is y1, y2, yn are independently distributed. Further, y1 is distributed as normal with mean mu and variance sigma square, and y2, yn are distributed as normal independent with mean 0 and variance sigma square. So we have already proved that we know that if y2, yn is normally distributed independent sigma square, then yi square upon sigma square is distributed as a chi-square 1, I running from 2 to n. So therefore, summation, because yi square are y1, y2, yn are independent, so their sums are also, it is independent of sum of square of random variables. It is also a chi-square with corresponding degree of freedom is, because there are n minus 1 observations, so we say that the degree of freedom is n minus 1. Okay. Further, we have proved that y1 is normal mu sigma square, then distribution of y1 square upon sigma square, it is a non-central chi-square with mean lambda, where, sorry, with non-centrality parameter lambda, where lambda is equal to mu square upon sigma square. And what is the mu square? In our setup, it is a summation I running from 1 to n mu I square upon sigma square. Okay. So further, we know that y1 and y2 yn y1 is independently distributed with y2 y3 up to yn random variables. Okay. So they are independently distributed. So their functional form is also independently distributed. That means we know that y1 square upon sigma square and summation I running from 2 to n yi square upon sigma square are independently distributed as non-central chi-square with 1 and non-centrality parameters lambda, and chi-square with n minus 1 degree of freedom respectively. Okay, so if they are respectively normal, then what is their sum? Sorry, they are respectively chi-square, non-central chi-square and chi-square, and they are independent. Then sum, what is their sum? Just yesterday theorem, if x and y are a normal, x and y are a normal with uh, mu1 and y's are the chi-square with n degree of freedom, then we have proved that the u plus v is nothing but, or x plus v, y is nothing but the non-central chi-square. So this is the independent chi-square, non-central chi-square with 1 lambda. This is independent with, it has the chi-square with 1 lambda, and it has the chi-square with n minus 1. So that means this sum we having the, using that theorem, it has a chi-square with 1 plus n minus 1, that is the n degree of freedom, and non-central parameter lambda, where lambda is equal to summation mu I square upon sigma, or you can write mu I upon sigma square, I running from 1 to n. And what is this? This quantity is nothing but, this quantity is nothing but, it is a summation xi minus, what is that? Okay. So this is in fact nothing but, if you multiply the sum this is nothing but, this is the y1, this is a y1 square. So you can write it as a summation yi square I running from 1 to n upon sigma square is distributed as a chi-square with n lambda. But what is the summation yi square? By the orthogonal property, you can write summation yi square equal to summation xi square. So just I am substituting here. Therefore, summation y square equal to summation xi square I running from 1 to n sigma square is distributed as a chi square with non-central chi-square with n degree of freedom and non-centrality parameter lambda, where lambda is summation mu I square upon sigma square, I running from 1 to n. So this is what we wish to effect prove. You can see here. Y equal to summation xi square upon sigma square is distributed as non-central chi-square with n degree of freedom and non-centrality parameter lambda equal to summation mu I square upon sigma square. So that is what we have proved. So here we have used the concept of orthogonal transformation to prove this theorem. Is that fine? Any questions? Simultaneously, you have to write. Otherwise, if you feel that at the end of the day I will see all the videos and will work out, so that is not possible. And 100% you will have etiquette in the distribution theory. Now we will discuss about the moment generating function of chi-square and lambda. That means non-central chi-square with n degree of freedom. So we know that the moment generating function is given by mxt is nothing but e raised to expectation of e raised to tx. So this is the form of a moment generating function. So e raised to tx expectation is nothing but, because we are using the non-central chi-square, it has the distribution, it has the range 0 to infinity, so it is e raised to 0 to infinity, e raised to tx fx of x dx. And what is fx of fx? It is a non-central chi-square. What is the PDF of non-central chi-square? It is nothing but r equal to 0 to infinity. It is a probability of the r as a Poisson random variable with parameter lambda by 2 into, for a chi-square 1 we have written chi-square 1 plus 2r. So here, because it is the n degree of freedom, that is a chi-square n plus 2r, and this is the dy. Okay, so we just take this r equal to summation is a free from the x, so we just transform, we just write the summation outside the integration. It is a summation pr lambda by 2 0 to infinity e raised to tx pi square n plus 2r dx. Sorry, it is a dx, not a y. So what is the distribution of MGF of chi-square? We know that if x follows not central chi-square with 1 degree of freedom, then the MGF of x is 1 minus 2t raised to, what is that? Sorry, it is a chi-square. What is that? It is a 1 minus 2t raised to, suppose it is an n degree of freedom, it is a minus n by 2. Okay, so we will use this same concept here. Here it is a chi-square n plus r is nothing but n plus 2r is nothing but central chi-square distribution. So it is a PDF of the central chi-square distribution. You can write here e raised to tx. What is the PDF? It is a 1 upon 2 raised to n plus 2r by 2 gamma n plus 2r by 2 into x raised to n plus 2r by 2 minus 1 into e raised to minus x by 2 dx. So this is the density of a chi-square distribution with n plus 2r degree of freedom. But we know that the MGF form is, this is the MGF for a chi-square with n degree of freedom. So here we have a chi-square with n plus 2r. So we can write it as a summation r equal to 0 to infinity. It is a Poisson of r random variable with parameter lambda by 2, and this is 1 minus 2t. Instead of the n, we have a here n plus 2r by 2. This is the MGF of the chi-square distribution with n by 2 n degree of freedom, and this is nothing but n plus 2r degree of freedom. So what is the Poisson form? The Poisson form is nothing but r equal to 0 to infinity. It is e raised to minus lambda by 2. Then what is that? Lambda by 2 raised to r divided by r factorial, and this is 1 minus 2t raised to minus n plus 2r by 2. So what will you write? This is just take the common 1 minus 2t raised to minus n by 2. You can just take the common, and you can also take the common as the e raised to minus lambda by 2. Okay, if you take this as a common, what will you get? It is a summation r equal to 0 to infinity this lambda by 2. Okay, and here it is a 1 minus 2t, and 2 to cancel out, so it is a minus r. It is a 1 minus 2t, okay, raised to minus 1, and that all bracket, because lambda by 2 raised to r, and 1 minus 2t raised to minus 1 raised to r, and this is upon a r factorial, this r factorial. So what we can write is a 1 minus 2t raised to minus n by 2 e raised to minus lambda by 2, and here you can write it as a e raised to lambda by 2t, 2 into 1 minus 2t. Why? Because this lambda 1 minus 2t I can keep inside or denominator, so it is a lambda upon 2 into 1 minus 2t raised to r upon r factorial. So we know that e raised to x is nothing but summation r equal to 0 to infinity x raised to r upon r factorial. So I have just used, and instead of x, which what is the quantity I have? A lambda upon 2 into 1 minus. So this is nothing but 1 minus 2t raised to minus n by 2. The base is constant, so it is a sum of lambda by 2 plus lambda upon 2 into 1 minus 2t. So we just take the lambda by 2 common, e raised to, let us say lambda by 2 is common. What happened? It is a minus 1 plus 1 upon 1 minus 2t. Okay. So what will you get? 1 minus 2t raised to minus n by 2 e raised to lambda by 2 as it is. This is 1 minus 2t is here, so it is minus of 1 minus 2t plus 1 upon 1 minus 2t. So just simplify. It is a e raised to lambda by 2. This is minus 1 plus 2t plus 1 upon 1 minus 2t. This 1 will be cancelled out, and this 2 will be cancelled out with 2. So it is a 1 minus 2t raised to minus n by 2 e raised to lambda t upon 1 minus 2t. So this is nothing but the MGF of non-central chi-square distribution with n degree of freedom, and non-centrality parameter is lambda. So what is the, if n equal to 1, then n equal to 1, that means when x is a chi-square with non-central chi-square with 1 degree of freedom and non-centrality parameter lambda, then the corresponding MGF is nothing but 1 minus 2t raised to, what is that,
minus 1 half.
minus 1 half e raised to lambda t upon 1 minus 2t. Okay, so this is the case. And suppose if you write non-centrality parameter lambda equal to 0, because we know that lambda is nothing but, what is the lambda is? It is a summation mu I square upon sigma square. So when the lambda is 0, because sigma is never 0, so when the lambda becomes 0, unless and until the whole mu I become the 0. If mu I equal to 0, which implies lambda equal to 0. So that means mu I equal to 0, so it will reduce the non-central chi-square into the central chi-square. And just when you substitute lambda equal to 0 here, what happens, e raised to 0 is 1. So you can have the MGF of a central chi-square. If it is n degree of freedom, so this is this. Okay, so you can easily reduce, or you can easily obtain the MGF of the central chi-square distribution by just substituting the non-centrality parameter equal to 0. So when we can write, when lambda equal to 0, which implies lambda equals 0, because mu I equal to 0, I equal to 1 to n, then MGF of non-central chi-square distribution reduces to MGF of central chi-square distribution. Okay, that is mxt is 1 minus 2t raised to minus 1 by 2 or n by 2 if you take this one, n by 2 and e raised to 0 into t upon 1 minus 2t is nothing but 1 minus 2t raised to minus n by 2. So this is the MGX of non central chi-square distribution. So one or two line questions may be asked from that. Is that clear? Now we know that if we wish to find out the moments, so rth row moment, this is called the row moment, is obtained by just take the rth derivative of MGF with respect to the t raised to r, or you can say that it's rth derivative of MGF and you just substitute t equal to 0, it will give the rth moment. And if you wish to find out the first moment, you have to just take the derivative of partial derivative with respect to t and just equate it to t equal to 0. You will get the first row moment, second row moment likewise. And then by using the relation of the row moments, you can find out the mean and variance of a distribution. So you can find out in the homework, obtain mu1 dash, mu2 dash, and mu2 equal to mu2 dash minus mu1 dash square. So just use the mu1 dash and mu2 dash, you can obtain the mu2. So this is the homework. You have this MGF, take the derivative, partial derivative with respect to t, and then equate it to 0. So we have studied also the cumulative cumulant generating function. Cumulant generating function is also known as the CGF. CGF? Okay. And it is denoted by the K of t. So what is the K of t? K of t is nothing but the log of MGF. So what is the MGF we have? MGF is nothing but 1 minus 2t raised to minus n by 2 into e raised to lambda t upon 1 minus 2t. So what is the log? It is a minus n by 2 log of 1 minus 2t plus lambda t upon 1 minus 2t. So that is nothing but the cumulative generating function of non-central chi-square distribution with n degree of freedom and non-centrality parameter lambda. So we know that if I write 1 minus log 1 minus t, what should I write? It is a, what I write? Anyone? It is nothing but the minus r equal to 1 to infinity t raised to r upon r, because it has the form minus t plus t square by 2 minus t cubed by 3 plus up to. And if you write here log raised to 1 minus t power minus 1, then it has a t plus t square by 2 plus t cubed by 3 likewise. Okay, so we have this form. And if you have the log of 1 plus t, then what happens? Here we have a odd terms are minus, here we have a even terms are minus. Okay, so this basics we know. So we will use that. What we can write by the log 1 minus 2t? So we can write it as a summation of r equal to 1 to infinity t raised to r upon r. Instead of t, here we have a 2t, so we can write 2t. So we can write kxt is equal to minus n by 2 minus summation r equal to 1 to infinity 2t raised to r upon r. And what about this? We can write it as a plus lambda t into 1 minus 2t raised to minus 1. Why? Because lambda t equals into 1 upon 1 minus 2t is in the denominator, so we can write in a numerator it is a 1 minus 2t raised to minus 1. And we also know about this It is minus minus plus, so I can write here it is a minus and plus it is n by 2 r equal to 1 to infinity with the 2t raised to r upon r plus lambda t, and this I can write it as a summation r equal to 0 to infinity 2t raised to r. Why? Because we know this 1 minus rho raised to minus 1 is equal to 1 plus rho squared plus up to infinity. So that is nothing but summation r equal to 0 to infinity rho raised to r upon r factorial. Sorry, not r factorial, because there is no factorial. Okay. So we have just here, we have instead of the rho, we have a 2t. So it is a 2t raised to 2r. But if I am interested to find out the cumulants, okay, so kxt also written as r equal to 1 because k small k, kr, r at cumulant kr into t raised to r upon r factorial. So when you find out the expansion and whatever the coefficient of t raised to r upon r factorial in that expansion, so that is called the kr. Suppose I wish to find out the first cumulant, then I have to see that what is the coefficient t upon 1 factorial. So that is named the first cumulant. So we try to write it in this structure. It is n by 2. Can I write it is a r equal to 1 to infinity. This 2 will be cancelled out with this. Okay, so this 2 is cancelled out with this, so it is a 2 raised to r की जगह पे क्या आएगा 2 raised to r minus 1. Okay, and if I am multiplying this with the r minus 1 factorial, then what happen here t raised to r as it is, so I have to multiply r into r minus 1 factorial. This I'll cancel out, so as it is 2 raised to 2r minus 1, 2 raised to r minus 1 into t raised to r upon r. So this is the just I have make the little bit. This is the lambda. This t I can keep inside. It is r equal to 0 to infinity. And if I will take inside, what happen? It is a 2 raised to r into tr plus 1. Okay, tr plus 1. So this is written as n into summation r equal to 1 to infinity 2 raised to r minus 1 into r minus 1 factorial into t raised to r upon r factorial. Okay, plus here if I replace r by r minus 1, if I replace r by r minus 1, that means r minus 1 equal to 0. Okay, if I'm replacing r by r minus 1, let me write r minus 1 equal to 0 to infinity 2 raised to r minus 1 and t raised to r. Can I write? And if I am writing denominator r factorial, so I have to multiply with the r factorial. So what I do, this is n summation r equal to 1 to infinity 2 raised to r minus 1 into r minus 1 factorial t raised to r upon r factorial plus lambda. This r minus 1 equal to 0, it is nothing but it is a r equal to 1 to infinity, it is a 2 raised to r minus 1 into r factorial okay into t raised to r upon r factorial. So if I write together, what I can write, it is a summation r equal to 1 to infinity n into r minus 1 factorial n into what happened here, it is a 2 raised to r minus 1, here it is a 2 raised to r minus 1, so it is a constant. Here it is a r minus 1 factorial, here it is r factorial, so it is r into r minus 1 factorial, so I will take r minus 1 factorial outside. Here it is a n, so this is the n as it is. Here what happened, lambda and r is from here, so it is a r lambda, and it is a t raised to r upon r factorial. If you compare r equal to 1 to infinity k r t raised to r upon r factorial, left hand side equal to right hand side, so you will get kr equal to this quantity by comparing the coefficients of t raised to r upon r factorial. We have rth cumulant equal to 2 raised to r minus 1 r minus 1 factorial n plus r lambda. Rth cumulants of chi square n lambda. Okay. Up to any questions, anyone? R equal to, of course, R is running from 1 to infinity. So, what is the first cumulant? If we substitute R equal to 1 in 3 star, we get the first cumulant K1 is equal to 2 raised to 0 into 1 minus 1 factorial to n plus 1 into lambda. 2 raised to 0 is 0, 0 factorial is 1, sorry, 2 raised to 0 is 1, 0 factorial is 1, and here it is a n plus lambda. And we know that the first cumulant is nothing but the mean of x. So whenever the x is a non-central chi-square distribution, what is the mean of non-central chi-square distribution with n degree of freedom and non-centrality parameter lambda? It is n plus lambda. Okay. Now second cumulant is giving you, what is giving second cumulant? It is giving the variance. So substitute r equal to 2 in 3 star, we'll get the second cumulant Q2 equal to 2 raised to 2 minus 1 into 2 minus 1 factorial into n plus 2 into lambda, because r equal to 2. So what happened? 2 raised to 2 minus 1 is a 2 raised to 1, it is a 2. 2 minus 1, it is a 1 factorial is 1, it is a n plus 2 lambda. So K2, and it is nothing but the variance of x. The second cumulative is giving the variance of x. That is mean and variance of chi-square n lambda are expectation of x equal to n plus lambda and variance of x equal to 2 times n plus 2 lambda. Now, if you substitute, if we take lambda equal to 0, that means when you take lambda equal to 0, non-central chi-square distribution reduced to central chi-square distribution. Then, what is the mean? It is a n, and variance is 2n. So this is nothing but the mean and variance of the chi-square with n degree of freedom. The next follows the chi-square, the mean and variance is this. Okay? Up to any questions, anyone? Okay. So now we will discuss about the recurrence relation. For cumulants. Since Kr, that is Rth cumulant we have obtained, it is nothing but 2 raised to r minus 1, r minus 1 factorial into n plus r lambda. We have Kr plus 1 is equal to 2 raised to r factorial, n plus r plus 1 lambda. So what will you get? What will you get? Anyone? Can we write in this 2 into 2r minus 1, r into r minus 1 factorial in bracket n plus r lambda plus lambda? Can we write? So what we can write? What about this? Let us say 2r. Here it is a 2 raised to r minus 1, r minus 1 factorial. It is n plus r lambda plus lambda. So can I write 2r, this multiply the into 2 raised to r minus 1 factorial, n plus r lambda plus 2r into 2 raised to r minus 1 factorial lambda. So it is nothing but, what is that? If I am writing this is common, okay. So this is nothing but your Kr. So it is nothing but 2 into, 2 raised to r minus 1, r minus 1, it is r, 2 raised to r into 2 raised to r into r minus 1 lambda plus 2r kr. This is kr plus 1 is nothing but this is the recurrence relation. Now you can verify. Suppose if you are substituting r equal to 1, what happened? K2 equal to 2 into r equal to 1. What is that? 0. So this is 0 into lambda plus twice of k1. And twice of k1, what is the k1? It is the twice of, what is the k1 for the, is it correct or any mistake? Here it is not the k2 equal to twice of k1. Here it is the lambda 2 is added. Something is missing. Any mistake from my side while calculation? Yes, it is r lambda. This is lambda, it is fine. Then any mistake? Okay, it is r into r lambda, huh? Which is r into r minus 1 lambda. Okay, now it is fine. So this is nothing but the 1. So it is a twice lambda. So it is nothing but twice lambda plus twice k1. Is it? अभी भी कुछ गड़बड़ है. I don't know. Twice lambda plus twice into n plus lambda. So what is that? It is a twice lambda plus twice n plus twice lambda. Okay. So it is a twice n plus 4 lambda. Now it is fine. It is a twice into n plus 2 lambda. K2 equal. Okay, so it is a 2 raised to r minus r into r minus 1 lambda. And here it is not the, here it is a 2r, yes, 2r is also there. Okay, so this is the cumulative relations for a non-central chi-square distribution.
सर यहाँ पर आर आपने ऐड किया वहां पर सेम ही रहेगा ना। आर माइनस वन मीन्स वन माइनस वन जीरो होगा है ना। तो लैम्बडा कैसे आएगा टू लैम्बडा।
बराबर. Let me check again. This is okay. So wherever the r, we substitute r plus 1, so it is a 2 raised to r. Okay, it is a r plus 1 minus 1, that is r factorial, and this is n plus r plus n plus r plus 1 lambda. Okay, then we can write it as a 2 into 2r minus 1. Why we have written? Because I am looking for this r into r minus 1 factorial. So this is 2 into 2r minus 1 into r minus 1 factorial. Okay, but why I have not written r minus 1 factorial here? This multiply r minus 1 factorial with lambda. So this is a factorial. So this is a factorial, and this is factorial. So it is fact, it is a 2 raised to r factorial lambda plus 2r here. Is it? अब सही होगा ना? When you take r factorial, so r 1 factorial is a 1, and 2 raised to, it is a 2 raised to r, yes, so r equal to 1, so it is a twice of this lambda, and this is r equal to 1 to 2 of k1. Okay, अब बराबर है ना? This is r factorial.
यस सर।
Okay, thank you. Okay, this is the r plus 1 cumulative. So this is the recurrence relation. Based on that, you can easily obtain the cumulates. Any questions? Anyone up to here? If no questions, then we will find the mean and variance by using the usual approach. Okay, this mean and variance we have obtained based on the cumulative relations. You can also obtain the from the MGF. Just take the derivative of MGF with respect to t and uh, take t equal to 0 in that form. It will give the first row moment. Take the second derivative of MGF with respect to t and substitute t equal to 0. It will give the second row moment. And based on the relation of the row moment, you can obtain the central moment. The first row moment is nothing but the first central moment. Okay, so second central moment is nothing but mu2 dash minus mu1 dash square. So you can obtain, or either you can have the cumulative generating function form, and based on that you can also obtain. Okay, let us obtain the mean and variance using the usual formula. Define. Okay, so I can ask in examination like that: define the non-central chi-square distribution and derive its density and obtain its two moments. So we know the part: obtain mean and variance of x when x is nothing but distributed as non-central chi-square with non degree of freedom, and non-centrality parameter is lambda. So we know that it is given xi is nothing but normal independent with mean mu I and variance sigma square I running from 1 to n. So we have already obtained the distribution of y is equal to summation I running from 1 to n xi square upon sigma square. It is a non-central chi-square with n degree of freedom and non-centrality parameter lambda, where lambda is equal to summation mu I square upon sigma square. So I wish to find out the mean of y. Okay. Keep this here, we have, let us say y. The mean of y is nothing but expectation of summation I running from 1 to n xi square upon sigma square, but sigma square is constant, so we can take outside, and because it is independent of sum of random variate, it is a sum of expectation. Okay, because x are independent, so we know that the expectation of sum of independent variate is nothing but the sum of expectation of that independent variate. So what we can write, we can write it as a variance of xi plus expectation of xi whole square, because we know that variance of x equal to expectation of x square minus expectation of x whole square. And what is the variance of x is given in our setup? It is given as a sigma square. And what is the mean is given? It is a mu I square. So this is nothing but the you can have. And just take sigma square inside, it is a summation I running from 1 to n sigma square upon sigma square plus summation I running from 1 to n mu I square upon sigma square. So this is nothing but the 1. So 1 is repeating how many times? N times. So it is a n plus, and this is nothing but the your lambda. Why? Because lambda equal to summation mu I square upon sigma square. So this is nothing but the mean of non-central chi-square with n degree of freedom and non-centrality parameter lambda. What about variance? Variance of y is nothing but the variance of summation I running from 1 to n xi upon sigma, is it? Or xi square upon sigma square. Okay. So because they are independent, so what I can take, it is a variance of sum of independent variates is nothing but the sum of variance of that independent variate. It is a variance of xi square sigma square. But sigma square is constant, so it is outside when variance of x by a is nothing but 1 upon s square into variance of x. So here we can take sigma square square outside, it is sigma raised to 4, I running from 1 to n variance of xi square. And variance of xi square is nothing but, you can written in this form, it is a expectation of xi raised to 4, that is xi square, where xi square is nothing but this, and expectation of xi square whole power 2. So this no, but we know that for a normal distribution, for a normal distribution, expectation of x minus mu equal to 0, which implies expectation of x equal to mu. Expectation of x minus mu raised to 2r plus 1 is always 0. All odd moments are 0, where r equal to 1 to infinity. And all even moments, x minus mu raised to 2r is given by sigma raised to 2r into 2r factorial upon 2 raised to r into r factorial. Or in other way, you can write it as a 2r minus 1, 2r minus 2, up to 3 to 1 into sigma raised to 2r, sigma raised to 2r as it is. If you just simplify this, you will get this quantity. So by using this, suppose if I am writing, okay, so what is my mu for? What is my mu for? This is nothing but, how will you find out mu 4? Mu 4 is nothing but expectation of minus mu raised to 4. And when I'm writing here 4, that means I'm taking r equal to 2. R equal to 2 is nothing but 4 minus 1 factorial into 4 minus 2 factorial. Likewise, 3, 2, 1. Sigma raised to 4. So what will you get? So 4 minus 2, not it factorial, it is a 4 minus 2. Factorial is not there. Okay. So 4 minus 1, then 4 minus 2, that is 4 minus 1 is 3. Okay. 2, 1 sigma. So what will you get? It is a, it is not the 4 minus, it is a 4 minus 2 or minus 3. So it is a 4 minus 3, that is the 3 into 1 into sigma square. Sigma raised to 4. So the answer is a 3 sigma 4. Okay. Further, what is the relation mu 4 equal to? We know that mu 4 dash is equal to mu 4 plus 4 mu 3 dash mu 1 dash plus 6 mu 2 mu 1 dash square plus mu 1 dash raised to 4. This relation we know. So just substitute. Mu 4 is in our setup, it is a xi raised to 4. And mu 4 is nothing but 3 raised sigma raised to 4. I said all odd moments. So here odd moments is especially, this is not the dash, this is the, yes, the odd moments is nothing but 0, because I told you here in the normal distribution So just substitute the 0. What it will give? This part is 0. And sigma mu 2 is nothing but sigma square, and mu 1 dash is nothing but the mu, and this is a mu raised to 4. This is the mu raised to square. So you will get 3 sigma raised to 4 plus 6 times sigma square mu square plus mu raised to 4. So substitute here, and this is nothing but the, you have already obtained what you obtain. So just substitute here 1 upon sigma raised to 4 summation I running from 1 to n 3 sigma summation expectation of xi raised to 4 is nothing but 3 sigma raised to 4 plus 6 times sigma square mu square plus mu raised to 4, and expectation of x square can be written as variance of x plus mean square. So and their square minus variance of x is nothing but sigma square, and mean is mu square and their whole square. But here we have considered it is a mean as the ith. It is not the constant. It is a mu I square. Okay. So just simplify this. 1 upon sigma raised to 4 summation I running from 1 to n 3 sigma raised to 4 plus 6 sigma raised to square mu I square plus mu I raised to 4 minus, this is sigma square, square is sigma raised to 4 minus 2 times sigma square mu I square minus mu I raised to 4. So this will cancel out, this will cancel out. What will cancel out? With here it is a 4, and this is here a 3. So we can get 1 upon sigma raised to 4 summation I range from 1 to n. It is a 2 sigma raised to 4 plus 6 times sigma square mu square. So just take the inside. What you will get? Sigma 4 cancel out. It is a twice, but how many times repeating? It is n times, so it is a 2n plus, you can take the 6 times sigma square cancel out. So it is a summation I running from 1 to n mu I. Sorry, it is a 4 times because 2 is cancelled out. It is a 4 times mu I square upon sigma square. So what is that? It is a 2n, and this is nothing but the lambda. So 2n plus 4 lambda, which implies 2 is common. So 2 plus n lambda. Sorry, 2 plus n. It is n plus 2 lambda. Okay, so what is that? It is a n plus 2 lambda, and this is nothing but the variance of y. So therefore, expectation of y is n plus lambda, no? And variance of y is 2 times n plus 2 lambda. So we have obtained in a different ways. Okay. So we'll keep today up to this. Any questions, anyone? No questions. I'll stop.